We have a problem here. It says an object moves along the x-axis according to this expression with x in meters and t in seconds. So we have x is equal to 10 minus 4t plus 2t cubed. So this is telling us the position of this object at given times t. I went to Google, I typed in the equation, and this is the graph that we have for this. Using this graph, we want to answer some questions. What is the object's location at t equals 0? So graphically, we can just look at the graph, go to time 0, and clearly we can see what the position is. You can also just plug in t equals 0 into the equation, and we should get the same answer. So if we do that, we have x of t equals 0 is equal to, we have 10 minus 4 times 0 plus 2 times 0 cubed. Both of these become 0, and we end up with 10. Next question, we have what is the object's location at t equals 2 seconds? So you try to answer this either graphically or by plugging into the equation. If we plug this into the equation, we have x at t equals 2 is equal to 10 minus 4 times 2 plus 2 times 2 cubed. This equals 10 minus 8 plus 2 cubed is 8 times 2 is 16. And so this is equal to 18 meter. Part C, we want to know what is the object's displacement between t equals 0 and t equals 2 seconds. Displacement is the difference in position. In part A and B, we found the position at t equals 2 and t equals 0. So now the displacement, delta x, is just the difference in those two positions. So that's going to be equal to 18 meter minus 10 meter. And so we get displacement is 8 meter. Next, we want to know what the distance traveled is between time 0 and time 2 seconds. So you might think this is just the same as displacement, but it's not. Let's start by looking at the graph first and see if we can figure out distance from the graph. So from the graph, we can see that we start at 10 meter at 0 seconds. Then we're traveling some distance to here, and then we're actually turning around, and then at 2 seconds we're ending up somewhere around here. So we can estimate our distance traveled from the graph. We have to figure out what this distance is. So we'll call this distance x1. And then we have to figure out what this distance is. We'll call that x2. And then the total distance we'll say is x1 plus x2. x1, if we estimate that, it looks like it's around 2 meter, maybe a little more. We'll just say 2 meter. If we estimate x2, it looks like we're going up about 7.5 meter. So we're going to say the total distance traveled is 9.5 meter. Comparing that to what we found for displacement, we found 8 meters. So we're saying distance is 9.5 meter, whereas displacement was 8 meter. And that's always going to be the case where displacement is either equal to or less than distance. We'll come back to this problem and see if we can't solve it using the equation. Next, we want to find the object's velocity at t equals 0. So we don't know how to do this using the equation yet, but let's see if we can figure out what this is looking at the graph. Looking at the graph, we're trying to figure out what the velocity is at the start. We know that if we have a position versus time graph, velocity is equal to slope. We can estimate the slope here because it looks like it's kind of linear for this interval. So we can estimate the slope here by finding the slope between those two lines. We'll get these 2 points by estimating them. This point looks like it's at 0.4, 8.3. The other point looks like it's at about negative 0.311. Using our 2 points, we can calculate a velocity. Using the slope formula, we get negative 3.9 meter per second for the slope, which should make sense because we have a negative slope, therefore a negative velocity. This is equal to the velocity at time 0. And again, we just estimated that, but we're about to learn how to find the exact value. We want to be able to get the exact value for velocity given position versus time equation or graph. Right now we know that velocity is the slope of position versus time graph. If we look at the example we just did, how could we increase the accuracy of the slope that we just found? If you want to increase the accuracy of the slope that we just found at time equals 0, what you would do is you would decrease this time interval. You would find a slope between 2 points that are closer together. The closer you are together, the more accurate your answer will be. If they're infinitely close together, your answer is going to be exact. So in calculus, we would say we're taking the limit as the time interval, delta t, approaches 0 of the slope, delta x over delta t. And the notation for this is equal to dx over dt, where whenever you see d by dt, d over dt of a function, that is a derivative. What we really need to know is that velocity is the slope of position versus time graph, which is delta x over delta t. And derivatives are just fancy ways of finding slope. So really we can say velocity is the derivative of x with respect to time. So now we know that velocity is just the derivative of position with respect to time. Given that, you can probably figure out that acceleration is the derivative of velocity with respect to time. In the next video, we will learn how to take the derivative of polynomials, and we'll take a look at our equation sheet, which tells you how to take derivatives of any of the functions that you might have to take derivatives of in this class. So what I want you to take away from this is that a derivative is just a fancy way of finding slope.